Good morning, dear students. I'm back again with another video. This video is for the note that I had already sent to you yesterday. That is about the gravitational potential energy, and especially the derivation part. And I'll be also talking about the books that is being recommended. So first, let us come to that gravitational potential energy derivation. Actually, in the derivation, we are using some mathematical formulas. Those are commonly known as the mathematical tools. So actually, before you start any derivation in physics, there are certain mathematical formulas that you need to understand first. Without those formulas, if we try to solve the problems of physics, especially the derivation, sometimes you may come across problems. So in this video, though I'm not going to go through all the details of those mathematical tools, I'll be just introducing the required formula for today's derivation. And in the last PDF note, in yesterday's note, Sir Joshua had already sent to you those formulas which are required to solve the derivations and especially the other numerical problems in physics. Those basic mathematical formulas like differentiation, integration and all, I have seen those, and if you go through those notes, that will be also very helpful. Okay, about the books, actually the book that is prescribed by the council is the NCERT book, that is for class 11 and 12, the NCERT book that you can easily purchase from the market. And if you want some additional book that is being called as reference book, you can buy from the market, like especially this book which is very popular, like Dinesh Millennium Physics. You can buy this. Actually it comes in two different parts, part A and part B. So this is just the part B or the volume 2, or you can try with this Pradeep's Fundamental Physics. This is also quite okay. Or you can try with this the Modern ABC. Just hold on, okay? I'm attached to the microphone. Here, this is the Modern ABC. You can try with this book also. So there are different options, and if you ask which one is the best book for you, actually all the books are equally good, and right now this is a bit early to differentiate among the books here. So what I suggest is, after you buy those NCERT book or the book prescribed by the Manipur Council, actually these two books are the same, only the cover is different here. So after you purchase that book, if you can afford, you can try these books. Actually these books are not that compulsory, but this will be good if you have it. And which one is best, which one is like worse, like something like that, I just cannot differentiate that because it is too early to tell those things. You will not be able to differentiate it properly right now. So only my advice is you try to get any reference book if you want. So the first one is you buy the NCERT book. The second is you can buy any of the books, reference books, like it may be the Modern ABC or the Millennium Physics or the Pradeep's Fundamental Physics. You can buy. Okay, this is all about the brief introduction of the books. Then let us go to the class, and I will be doing one more derivation for the gravitational potential energy. Okay, then we'll move to the class right now. So we are back in the class. We'll be deriving this relation, that is gravitational potential energy. This is our derivation. And before you talk about this, let me just remind you one more thing here, that is about the laws of gravitation. In the laws of gravitation, we have two mass m1, m2, separated by a distance r. Okay? Then the force of attraction between the two masses is given by F is equal to Z m1 m2 divided by r square. This one you have already learned in the previous class, so we'll be using it one more time. Keep this formula handy, we'll be using it again. So this is the first formula that I'm introducing, and before I actually start the derivation, I need to tell you about a very important mathematical formula that is going to be used in this derivation. This is the basic formula from integration. I'm not going to explain everything in detail right now. Let the concerned mathematical teachers, your mathematics teacher, let him explain it in a better way. Okay, in integration, as we go with the definition, it says that this is the inverse process of differentiation. Inverse process of differentiation. It says inverse process of differentiation. Inverse process of differentiation. But the problem is you have not learned about differentiation again. Okay, this is the main problem. So I hope that you have gone through the notes, the PDF note that was sent to you by Sir Joshua. You please check it one more time. And he had already sent some notes on differentiation. So you go through with that. So in this class, I'm not going to explain everything like this because this will be a very, very exhaustive class again. So what I will be doing is the requirement only in today's derivation. So let us not talk about the differentiation, this and that. I mean, let us not talk about the definition, this and that here. I'll come to the point integration directly. I'll explain in a physical way, not in definition, but in a very simple example. With a simple example, I'll explain this physical way. Suppose you have a rope. Let us say this is a rope, R-O-P-E, rope. All right, and the rope is divided into small parts, equal parts here, like this. Say each part, the smallest part, remember all of them are equal, okay? So is dx here. One part, the smallest part is equal to dx. This is also equal to dx. This is also equal to dx. So if you cut out a piece, the piece is dx here. Okay? So you are going to combine the different pieces together, and finally let us think that the length of the rope is x, for example. So what do you observe from the figure? If you combine the small part together, you get the whole length of the rope here. So this is what we call as the integration now. So what we do is we'll just take a small part here. This is what dx. Okay, just taking the smallest part here dx, and I'm just doing integration here like this. This is what integration. As the word says, integral. Integral means making it bigger. Then once you do integration, you should be getting the whole length of the rope. That is what? X here. So this is your basic formula. Similarly, integration of any function here, dy should be also equal to y, like dp also equal to p here. This is one fundamental formula of integration. We'll be using it later on. Okay, I'll be writing the direct formula that is to be used in our derivation of gravitational potential energy. The formula says like this: integration of x and dx. This is equal to x, the power increased by 1, n plus 1 divided by the power again, n plus 1 here. This is the formula. And if your integration comes without any limit, this is known as indefinite integration here. But I'm not going to talk about this indefinite, this and that. This will make you more confused here. So just take the formula like this: integration of x and dx is equal to x power n plus 1 divided by n plus 1. And remember, in this case, there are no limiting values, so it should be indefinite integration. On the other hand, if it comes like this, x and dx with the limiting values from a to b, it should be x, the same formula, x here, increase the power by 1 divided by n plus 1. Then whole, keep it inside a bracket, the third bracket, and put the limiting values now. The lower limit is a, the upper limit is b. In other words, lower limit is the starting point here. You can say it is the start, and this one is the finishing point here. You can say that. So there should be two limiting values in indefinite integration here. So this formula is very popular in physics. We'll be using it many times here. And let us see the expansion. How do we expand it again? So after you write this formula, what we do is we need to continue again here. This is still equal to, let me write here. This is still equal to, take this x here. So instead of this function x here, you replace by the upper limit. Instead of x, you write on b here. So it becomes what? b n plus 1 divided by the same increasing power n plus 1. This will be followed by a minus sign. And instead of x, you replace by the lower limit. That is, instead of x, you can write a now. A power n plus 1 divided by n plus 1. So this is your formula, the formula that we'll be using it. I'll just give you one example. Say integration of x power 5 dx from 1 to 2, for example. How do you expand this? By the formula, it can be expanded as x here, as with the formula, n plus 1. The power is 5 here, so it should be 5 plus 1 divided by 5 plus 1. Then the limiting values, the lower limit is 1, upper limit is 2. So I write like this. This is equal to x power 6 divided by 6. Then 1 to 2 again. So your next step is put the upper and the lower limit. So instead of x, you can write 2. So it becomes about 2 power 6 divided by 6, followed by minus. Instead of x, you can write 1 here. So it becomes 1 power 6 divided by 6. So this is your answer. You can expand it here. So this is the way how we solve problems using this definite integration. So now let's come back to our derivation. That is the main derivation for today's class. In gravitational potential energy, look at this. Before you talk anything about it, just look at the diagram here. Say, here is a mass, for example. This may be earth here. Let us say this is earth. Then you take a point P here. Take a point P. Then, from a very far place, how far is that? From infinity far, infinite far here. From infinity, you bring a mass m, just like a small ball, you bring it from infinity. Keep on bringing, and keep at the point P. Okay? Once you keep at the point P, you have performed a work. What type of work? The work in bringing. bringing the mass up to where? Up to the point P. So this work done is what we define as gravitational potential energy here. Okay? So in definition, how do we write this? The gravitational potential energy at a point is defined. This is defined as the work done in moving, or you can say displacing, in moving a body of mass m, let us say, from infinity up to that point. That point means what? The point you choose here. That point here. So this is the way how we define the gravitational potential energy. Okay, I'm just filling up the ink here. So this is the formula. This is the definition of gravitational potential energy. Now, using this concept, let us try to derive now. Suppose here is a mass. Let us say this is m1. You keep at the point A, let us say, and you choose another mass here, m2. Keep at the point B right now. Remember, you can bring the body, you can move it away, or you can bring it here, no problem. Okay, you can still bring it, or you can move it away here. So let us look at this system. You have m1, m2, and take one more point C here. This is C. How far is the point B, or how far is the mass here? Let us say this is R1. I keep here at R1. Okay, then you need to move it now. You have to move from B to C up to a final distance of R2. Remember, this mass M2 should be moved from here to here, and this one is kept at rest, not moving this one, but simply move it from B to C here. So in moving from B to C, you have done a work, is not? So that work done will be known as gravitational potential energy of the system here. This is the meaning. Okay. Before we actually start moving from B to C, let us think that one point is here, say D, and you can move out to E again here. Keep in mind, we have to move it from here. The body moves, it must be moved from here, from B to C, okay, actually B to C. But before that, move it from D to E here through a small distance of dr. And let us assume that our mass is right now here for the starting. Let us think that the mass is here right now. What mass? M2 is here right now here for some time. M2 is here. Okay, so this is at a distance of r, let us say. Listen carefully, alright? Otherwise, this will be a bit difficult to understand here. Actually, you have to move the body from B to C. It's not that. B to C, but before you move from B to C, just keep the body here at D and start moving from D to E. That is the meaning. Your aim is B to C, okay? But before that, you move it from D to E first. That is the meaning. Now, if the body is kept at the point D right now, the gravitational force should be equal to, F should be equal to Z, the two mass is here right now, M1, M2 divided by the distance is what? R here. You have to write R squared. Like this. So let's call equation number 1 here. And let us see how much work is done. Remember, you are going to move the body from D to E now, from D to E like this. So in moving this one from D to E, you have to do a small walk. The small walk is dW is equal to, walk done is the product of force and displacement. So the force would be F now. The displacement is what? dr here. Remember the gravitation, the laws of gravitation says that these two bodies should be what? Attracting. It's not. This is attracting here, but you are moving against the attraction. Is it okay? They are attracting like this, but you are moving it against the attraction. It means work has to be negative here. So you can put minus here. So this is equal to G m1 m2 divided by r squared and what? dr. So this is your equation of work done. Call equation number 1 here. And if you have a system just like Earth and the moon here, this is your moon. Between Earth and moon there is a attractive force here. Attractive force is there. Okay? So because of this attraction, energy comes here. So the whole energy of the Earth-Mars system, energy is taken as negative. Simply because there is what? Attractive force. We call it as a bond system, like binding each other. So because of this bond system, the energy, the potential energy is always negative here. So in the same way, if you move it from B to, if you move it from D to E here, D to E, there will be a small energy. So the change in energy, in potential energy, let us say, this will be equal to what? dU again, which is also going to be negative here. As I said, why is the potential energy negative? Simply because there is attractive force between the two bodies here, because of that. Okay, I miss minus sign here. Now, the definition says that the work done in moving the body, is equal to what? Gravitational potential energy. Okay? It means this equation number 1 and equation number 2 should be the same. Why? Because the definition says that work done in moving the body is equal to gravitational potential energy. So equations 1 and 2, they must be what? Equal. Okay? So if you compare this, what the two negative sign will cancel. Therefore, your potential energy is equal to the work done is simply equal to G m1 m2 divided by r squared and what? dr. You have this equation. Okay. Next. What if you move the body from B to C? Remember, this equation is what? From D to E only. Okay. But if you move it from B to C, let us see. Therefore, work done in moving from where? B to C now. B to C now. This will be equal to. Remember, this is a small part. It's not. Small part now will be becoming bigger part. So as I said before, if small quantity is to make it bigger, you need to do integration. So once you start saying that I want to move it from B to C, you have to start doing integration here. Otherwise, if you just simply move it from D to E, no need of integration. Okay? So now I'm going to move the body of mass M2 from B to C. That is why I have to do integration with that. So integration of dW here, PE was, you can write directly here, no problem here. PE, instead of PE, you can write DU. It's not DU, integration of DU. Okay, here. This negative already cancelled before. Alright. So DU is equal to, on the right hand side, you have Z M1 M2 divided by R squared and what? dr. Remember, you have to move it from B to C. Okay? So in moving from B to C, the initial energy before you move it, okay, say it is 0, And when you reach that point C, the energy becomes total energy right now. So you can write 0 to u. Or if you find confusing here, no problem. Integration of du is equal to what? U is not that. U. This is okay, fine. You can keep like this. Integration again. Z m1 m2 by r squared dr again. But remember, let us see from where are you moving. You are moving from B is not. B to C, right? How far is B from the point A? B is R1 far. So starting is R1. B is at R1 and you move up to C. How far is C here? C is R2 far. So it should be up to R2. Okay. This is your formula. So after this, factorize now. Or you can write U is equal to Z constant, M1, M2 constant. Because this constant Z is, as you know, universal constant. The value will not change. What about mass also? The mass of a body is constant. So you can take it outside integration now. So you can take it now Z M1 M2. Then what happened? Integration of 1 by r squared dr. And starting from R1 up to R2, which is equal to Z M1 M2 again. So if you bring it up here, it becomes what? R minus 2 dr from R1 up to R2 again. Now simplify this using your formula of integration, which is equal to, let me still write the constant now, Z M1 M2. Then if you do integration now, this will be, as I said before, integration of x and dx is equal to x n plus 1 by n plus 1. Using the formula here, you can write now r power is minus 2. So it becomes what? Minus 2 plus 1 divided by minus 2 plus 1. So the limiting values are from R1 up to R2. I'm not doing anything, okay? I'm just using the formula here directly here with the limiting values R1 to R2. So now simplify this. You have Z M1 M2. Then what? This will be R minus 1 by minus 1. Then what? R1 up to R2. You have this. Okay. Then this is further equal to Z M1 M2. Now you can write this minus here and this R power minus 1. R power minus 1 can be written as 1 by R here. So you can write 1 by R. R1 up to R2. Okay, this is going to be a bit long because this is essay question, which is equal to Z M1 M2. Then what? Minus 1 by, instead of R, you replace by upper limit, becomes what? R2 minus. You bring it, hold this term again, minus, still bring it now, 1 by R. R will be replaced by the lower limit R1 here, like this. So it becomes minus 1 by R2. Minus minus plus 1 by R1 here. Okay? So now, I missed this part. Z M1 M2 by okay, only this is missing. So therefore your energy now finally becomes Z M1 M2. What is left inside the bracket? 1 by R1 minus 1 by R2. Okay? So if you take, just do some substitution right now. If R1 is infinity and R2 is equal to R. Just say like this. If you take these two values, then U becomes what? Z M1 M2 inside the bracket. What is left? 1 by R1. R1 is replaced by infinity minus R2 is replaced by R here. So or finally you have Z M1 M2 divided by 1 by infinity is equal to 0. So you have this minus here. This will be multiplied here. So minus R here. So this is the equation of gravitational potential energy for a system. of two masses m1 and m2. Okay, this is our derivation. Remember, one of the two values r1 and r2, one of them is taken as infinity. As I said before, one has to be at infinity. Like you are moving the body from infinity to that point. So one of the two should be infinity here. So I'm just putting this as infinity, and the other is r. So our equation becomes like this. I know still some of you have still some doubt about it. And remember, in physics derivations, especially this type of bigger derivation, you are not going to clear 100%. Okay, 100% will be cleared only when you study it or when you revise it repeatedly. So looking at the first derivation here, first time derivation, your learning should be at least 60 to 70%. If you can learn this much, that is good. That is a good sign. And the remaining 30%, you will be learning it after you revise it repeatedly again. Okay, this is our derivation. So for today's class, I'll stop here and see you in the next class again.